I just feel like it's a very community-driven conference. It also has a lot of quality, and people are just nice. Hi, my name is Sarah, and this is Asian Conf in Dornbirn.
Amazing venue. Austria is beautiful. Meeting all of the people in the community and getting to go and hang out and ski.
All right, as she mentioned, building offline first apps are not easy. And I'm gonna be really talking about two things. The first is building offline first applications. And I think before we talk about actually doing this, we should talk about what this actually means. So I kind of picked up three definitions off of a combination of the internet and kind of my own ideas. So the first is this. The core features should function with or without an internet connection. You know, that's pretty obvious. That doesn't mean the entire app has to function without an internet connection. It just basically means that we have a core subset of features, we have a core subset of functionality. We want this to work. We also don't want the app to crash. We don't want things to break when we're not connected to the internet. The second is this. We'd like to have this idea of where we're writing our data locally, and then once the end user's device then periodically uploads and replicates the data to the cloud or to whatever database that we have connected to our app. And when you start taking this idea or these considerations into consideration, you kind of start thinking about building these types of applications as in building more of like a distributed system. The third thing that this basically means is that we, if you're building an offline first application, you end up wanting to provide end users with a consistent user experience, of course, regardless of whether they're connected or not, but also they might have a slow internet connection and they might then have a fast internet connection. They might then have no internet connection. So kind of taking all of the different variables of like while they're connected, while they're not connected, as their internet connection gets better and worse. And at the end of the day, most of the time, these offline first apps are gonna provide a good user experience or a better user experience than applications that are kind of not optimized for being offline first. And then the second idea I wanna talk about is building real-time applications. So a couple of definitions here. The first is that a real-time application, what does it mean? It basically means an application that functions within a time frame that the user senses as immediate or close to it. When you think about this type of application, you might think about something like a chat application where you're talking to someone, you send a message, that next response basically comes through. You're not having to refresh the app. You don't have to kind of go back and forth to retrieve new data. The data kind of like comes through directly. You also might think of something like Google Docs. Google Docs, you may be collaborating on a spreadsheet with someone. You're typing in this cell, they're typing in this cell. You might have even a half dozen users in the same document. They're all typing at once. You don't have any errors. You're kind of seeing the movement as it happens. And then the second is when you're building a real-time application, you're not really thinking of building your app in a traditional way. You're kind of, in my opinion, thinking of it more as a cohesive system where data is in sync across all of the connected devices. So you might have dozens or hundreds or even thousands or tens of thousands of connected devices, and you want to make sure that the data that you have on your device ends up being propagated to all the different devices that are also connected to the same system. So what my talk is really about is, in my opinion, when you're building real-time applications and when you're building offline first applications, okay, I just want to make sure my animations are working there. When you're thinking about building these two types of applications, there's a lot of overlap in the functionality and there's a lot of overlap in the considerations. And I think when you're building, this type of application, either real-time or offline first, if you can kind of merge the two into something that works really great, you end up kind of with what I kind of consider modern application development. So, welcome to my talk. This is the future of real-time offline data. My name is Nader Dabit. This is my avatar on Twitter if you've seen me there. And I do a lot of stuff. The main thing I'm kind of working on and I'm pretty happy about and want to talk about today, I guess, is my book, Full Stack Serverless from O'Reilly Publications. This book is about building full stack apps on the cloud using GraphQL, React, and AWS. So before we talk about how to do this, let's talk about why we would want to do this. So why would you want to build a real-time and offline first application? Well, the first thing, like I mentioned before, is this idea of modern application development. And what does modern application development really mean? Well, a lot of the apps that we're building today kind of fall into this category, so you might not even call it modern application development. It might just be application development. These might just be the types of apps that you're kind of building on your day-to-day basis anyway. And I think the number one category that you kind of see here that falls into this is collaborative apps. So the more that we have better tools that are available for us to build these types of applications, the more features that people are adding, and the more that you see these types of collaborative apps coming into the wild. Again, another reason you might want to do this is that you want to build an application that is available to everyone in every part of the world. You want to be able to deploy not only here in Europe or in America where we have a really, pretty good internet connections in general, but you might also want your app to work in parts of the world where they don't have a good internet connection. They also might have really slow devices, and you might have to take, all of this stuff into consideration, and you want to provide some way for your app not only to work there, but you also might want to provide a decent user experience, if not a great user experience. And the last thing is user experience. So again, when you're building these types of applications, a lot of times, one of the things that you're really doing is doing this idea of an optimistic response and optimistic user interface, optimistic UIs. So when you're building these apps, when you create a mutation, when you create an update, you see the update happen immediately, and it just feels really snappy, it feels really fast. Now, when you do this once, if you're just building like a to-do app or something basic, it's pretty easy. But when you start building something sophisticated, when you start having to take in all of the considerations that you typically do, authentication and authorization, you have to take into consideration all of the different pieces of your application. This starts becoming pretty complex. So the idea here that I want to talk about is some of the things that we've done at my company to kind of make this easier and share some of the ideas that we've had, and hopefully that, listening to these ideas, that people can kind of take some of the ideas that we've learned and maybe apply those and create something similar to the thing that I'm going to be talking about today. So what are some considerations technically when you're building these types of applications? Well, one of the first and the hardest and the thing that we're going to focus a lot really on today is caching and this idea of caching. And I guess not only caching, but local persistence in general. You may have heard this quote, there are only two hard things in computer science, cache and validation and naming things. Dan Abramoff, he didn't say that, but we can attribute it to him. And when we're talking about caching, we're not talking about caching on the server, we're talking about caching on the client. And there's a couple of pieces that come into play here. The first is data synchronization. When you have different actors in different parts of the world and we're all operating against the same system, what we're going to end up happening is we're going to have data conflicts, we're going to have inconsistencies, we're going to have people, again, going offline, coming back online, and what we're going to need to do is find some way to synchronize all this data and do it in a very consistent way across all of the devices connected to the system. We also want to have complex querying. When you think about caches, you typically think of having some type of local data, either in memory or some type of local storage, where you're have maybe some initial subset of data that you've queried against and you've stored locally, and then you might need to get additional subsets of that data. As your application continues to evolve, you end up updating this data. People might be making changes elsewhere, you're updating that cache, and then you want to then take other subsets of that data for your own application, and you might want to query against it, you might want to do things like get additional or maybe remove parameters that you're not actually rendering in your app, things like that. And this starts to become pretty complex when you're working with the cache. And then when you're actually implementing all this stuff, what you end up with, if you're doing it yourself and you haven't created a good abstraction, is you have a ton of additional complexity in your code. You're writing caching mechanisms, you're reading and you're writing to the cache all over the place, and then you need to re-render and send updates to any parts of the app that are also using this data. And I think one of the things that we end up doing is we start treating our cache as a database or as a data store. Caches weren't really created to be that. They're just created to have whatever data that we'd like to then retrieve quickly, have it available, but we're not actually, we don't have all the different querying mechanisms that we typically would on a typical database. The next idea is, again, synchronization. I talked about this a moment ago. When not only do you have all of these people doing different things in your app, you also want to make sure that when these updates happen, you're only sending the data to the right devices that actually need the data. So in a real-time application, this might be something like a chat app where you're in a chat room and you have another person in the chat room and they're sending a message. You want to be able to filter that data and only send this new data to the clients that are subscribed to those changes. If you're thinking about something like Google Docs, you have authentication and authorization things that are concerned. So if you might be on a document and there might only be a half dozen people that are authorized to see those changes, you need to actually take all of that into consideration and only send updates to the people that are supposed to see these updates. And you also don't want to send updates where they're not needed, and you just save bandwidth. And then one of the big pieces about building these types of applications is this idea of conflict detection. So if you have two people sending data either at the same time, or you might have someone that creates a mutation while they're offline, someone else creates an additional mutation in the future, they're online. When the other user comes back online, you're going to end up having some type of conflict. How do you detect these conflicts? And then conflict resolution is how do you resolve this conflict? And how do you do this, again, in a consistent manner? You need to make sure that, over the course of your application, you're not having any errors, having to do with ordering and things like that. And this is a very, very hard problem to solve. Another consideration are the idea of multiple platforms. If you've ever used Google Docs, you've probably been able to edit your document from your computer. You can even use the app on your mobile phone or a tablet, and you're able to do this from all these different clients. Doing this is not really easy, again, because if you have a native iOS app, a native Android app, you have a web app, and maybe whatever else, maybe React Native, you end up rewriting all of these caching mechanisms, all of this logic locally multiple times because you need it to work consistently across all these devices. So you're bringing even more complexity there. And then finally, scalability. So when you're building something simple, you might have a half dozen or so connected devices. This is pretty easy, but when you start building, complex systems, you start thinking about scale. You start thinking about what if we end up having tens or hundreds of thousands of connected devices? How can we actually scale this? A lot of the companies that we work with have these problems, and we've really taken these into consideration around some of the things that I'm going to talk about today. We've worked with, just with this system I'm going to talk about today, with companies like Ticketmaster, Aldo, and BMW, where they have literally millions of connected devices, and we have to make sure that none of their applications break and nothing is leaked. We have to make sure all of their data is secure. So how can we actually accomplish scalability as well? So now that we've talked about the considerations, let's talk about some of the solutions that I'm going to propose today. The first, again, about caching. We talked about this a moment ago. So we talked about the problems. Let's talk about some of the solutions. If you've ever written a cache in GraphQL, you might have seen something like this. In this example here, we're creating a mutation. We're saying we want to create a new comment. We then want to create an optimistic response. So we then create another separate little function or an object where we're kind of describing the data that we would like to see in this optimistic response. We then need to write to the cache. So we first read from the cache, we then write to the cache, and we write to that copy of the cache, and then we rewrite to the cache. So we're creating a lot of complexity here just for a fairly simple operation. So what we're basically doing is duplicating, our logic. We are saying we want to create an item, and we now need to make sure that this operation happens in two different places. We want to write to our system, which would be the cloud or wherever our database is located, and we also want to write locally, and we want to keep these things in sync. And those are writes, but what about reads? We want to be able to query, again, from our local database or our local cache, whatever that is. And once you create this initial query from your database, you store it locally, you are stuck with that basic subset of whatever that data is. Let's say you now want to create an additional query where you only want to filter against something. You might want to say, okay, I have all of this data. I want to then just create another GraphQL query against what we already have here. This just isn't going to work. What you could do, I guess, is you could take all of that data that we've already queried locally and then maybe take that and then filter it and then use that in a place that you like to use it, or whatever else that you like to do. But really, you're basically stuck with this initial query that you have. This initial subset of data is kind of what you're working with. Now, the same thing happens when you're talking about subscriptions. So with mutations, you're creating the mutation, you're creating the cached or the optimistic response, and you're writing it to the cache. With subscriptions, or when you're dealing with real time, you have this listener, you have the data come through. You then have to write again to the cache, and this 20 lines or so of code here is just a traditional or a typical thing you might see done if you're working, with GraphQL. So I think the answer to this is, what if we don't need a cache in the first place? Maybe what we need is actually a store. So instead of thinking of a cache, we do need to think about this a little bit in a more sophisticated manner. And what we need to do is think about this as a store. And at the most basic level, to me, working with data locally is a very simple mental model. If you've ever taken a React tutorial or a Vue tutorial or any tutorial, the first thing that they're going to do is create some local state in memory, and you're just going to be writing and reading from this local state. This is pretty simple because all you're doing is creating updates, you're rendering this data, and you're not really having to think about anything else. This is a very great user experience, and it's the reason that we use this idea whenever we're creating tutorials and we're getting people started, because we want to start them off in the most simple way as possible, right? What if we took this mental model and applied it to a distributed system, and we applied it to building real-time and offline applications? Well, that's basically what we've done. We decided this is the best programming model that we would like to work with, and we want to make this work in a distributed fashion. What we've done over the last 2 years, and we released this in December at reInvent, and I'm going to talk about how we built this, and hopefully not only will you learn, some of the stuff that we've done, but we also would love to see other things in this category, people building similar solutions. So what we've built is Amplify Datastore, and it's a multi-platform, on-device persistent storage engine that automatically synchronizes data between mobile and web applications and the cloud, and we use GraphQL to make this work. So the way that this works is this. It all kind of revolves around this programming concept of dealing with your data model, just like I talked about a moment ago. And we kind of decided that GraphQL schema definition language is the perfect way for developers to do the data modeling in their apps. And it's also kind of the perfect way to solve this problem of real-time and offline application development in a cross-platform manner. So the idea is that developers, or you, will define your data model. We then translate these models into what's needed at both the local storage repository level as well as the backend for interacting with the system. And in our case, the system would be AWS AppSync, which is a managed GraphQL service. So we'll walk through this in detail. So you, as a developer, want to create an application. You author your GraphQL schema. So let's say we want to create like a blogging application. You create a post type. You give it a couple of fields, an ID, a title, and a description. Once your data model has been defined, you run a build. Now, depending on which platform you're on, this could be an NPM script, it could be a Gradle task on Android, or if you're building an iOS app, it would be something like an Xcode build phase. Out of the build, we then generate models with the language construct of choice. So for JavaScript or TypeScript, this would be a class. If you're working with Java, it would be a JavaScript Cocos. And if you're working on Swift, this would be a class. Now, you as a developer are going to be interacting with these models that you've created, and you're no longer going to be having to deal with or program against GraphQL. Instead, you're operating on what we have as the Datastore API. The Datastore API offers this idea of a fluent interface. So what we're going to do is we're going to import this store API, and we're going to then be able to create updates, mutations, queries against the store. So let's say we want to save an item to the store. We say store.save. We just pass in the properties we'd like to save. We can also query against the store. So we want to query all the posts. We can then just query store.query, passing in the model that we'd like to query for. If we'd like to have conditional logic, we can use predicates. So say we want to query only the posts where someone has written formic rules as the title. We can do that, where we're just passing in the query as the first argument and predicate as a predicate function as the second argument. We can also chain predicates. So let's say we want to query our store where post title equals formic is awesome, and the post status is published. We can do that as well. And we can also create updates, of course. We want to create deletes or updates. But the cool thing about this is we can actually apply predicates to the updates. So we might want to say we only wanted to delete an item based on this predicate, or we might only want to update an item based on that predicate. So here we're basically saying we only want to delete the post where the post status equals published or whatever. So let's take a look at the vertical slice of this architecture and how it works. I showed you this a moment ago, but we're going to look at it a little more in depth now. So after you create a model instance, the library basically decomposes that model instance and creates, in what we call a storage engine component, a model registry. The model registry is basically a registry containing all of your models. And, we then have an adapter, a storage adapter, and the storage adapter is using a classic repository pattern, and we convert this into the persistence layer of choice. So if you're working with the web, it would be IndexedDB. If you're on native iOS or Android, it would be SQLite, and then we're also working, and we'll soon have a React Native version of this, which will be either using async storage or a bridge to SQLite. Doing this, you can use this without an AWS account. If you only want to use the offline storage piece and a nice way to do data modeling and programming against all these filters, you can do that without an AWS backend because, again, this is all just a local persistence layer. But if you want to then sync this with your AppSync backend, all you need to do is update a flag in your build script. And what's going to happen is you'll then be connected to the system, and you'll be working against the storage engine with the Datastore API, which in itself is working with this idea of a sync engine. You're basically going to be creating writes to the sync engine. The sync engine is then going to basically take these writes and create GraphQL statements. So queries and mutations will go against the actual the GraphQL API. And then we'll also be observing data. And then under the hood, this is going to be working with GraphQL subscriptions. And any responses are basically converted back to the model from GraphQL and then written to the storage engine. So that's the offline piece. Let's talk about the real-time piece. So what are some options for real-time applications? First of all, there's long polling. This is probably the most basic way that you can do this. And it sounds just like it is. You have some type of time interval where you're going to say, I want to hit this API every 5 minutes, every 10 minutes, every 1 hour, or maybe every 1 second. And we want to just get data and check and see if the data is changed or not. This isn't very efficient because let's say you have a change every 1 hour, but you only are querying every day, or you might have a change every second, but you're only querying every hour. So you're going to end up overfetching or underfetching in some way. There just is no other way around it. Another option is server-sent events. So server-sent events basically have a couple of characteristics. They only allow communication to the server, from the server to the client. So there's no protocol from the client to the server. You're limited to UTF-8, so you can't actually send any binary data with server-sent events. And you also have a limit of 6 event source connections at a time. And this is like a hard limit. They're never going to change this based on some conversations that I've seen online. It is part of the native browser event source API, so it's part of the native local API, and it's actually a pretty simple API to work with. But it's not that well supported, at least as much as something like WebSockets is concerned. So let's talk about WebSockets. WebSockets are another way to deal with this. This protocol does allow data to go both from the client to the server and from the server to the client. And using WebSockets, you can work with both binary and UTF-8. There's more robust browser support than server-sent events, but the API is a little more complex. But because there's a lot bigger of an ecosystem, there's a lot of good abstraction around WebSockets these days. And then finally, the other mechanism that we use is GraphQL subscriptions. So GraphQL subscriptions are a real-time, event-based way to send data from the client to the server to the client in real time. They're event-based, and typically the events are based on some type of update or some type of mutation. So you might say on create, on update, or on delete. I want to then send this updated data down to whatever clients are subscribed, and you can even filter these subscriptions based on some types of arguments. And these are initialized on the client. Typically, this is done via WebSockets, but the actual implementation is up to you. This is only kind of it's not an actual implementation detail. GraphQL is more of a spec, so you can kind of do this whatever way you like. And then when the event happens, the server then uses this open connection to send the event data down to the subscribed clients. So how did we deal with this idea of real-time, these real-time GraphQL subscriptions? What type of abstraction do we have? We have this idea of observe. So we basically can call datastore.observe. We pass in the operation or the class that we'd like to observe, and then we can basically subscribe. And we can see the event, and we have information about the event. So we can look at the operation type, the model, and the element. You can also pass different arguments into this subscription to basically filter based on whatever arguments that you like. Now, this is basic. This is just like a basic idea in general, but what does this actually give you? Well, this actually does away with a lot of that boilerplate that we looked at before. And what this basically will end up giving you is this idea of a single rehydrate query. You don't need to, and again, you don't need to then continue working, worry about working with updating your local store. All of this is handled for you by the system itself. So let's take a look again at what we used to write for GraphQL subscriptions, and let's see what we can do now to kind of update this using this idea of a single rehydrate query. Instead of creating the actual cache update ourselves, we're just going to listen to any subscription event that comes through. And anytime that happens, we're just going to refetch our posts because the local data store has already been updated by the system itself. So we don't actually have to worry about going and caching updating the cache because the store has already been updated. All we're basically doing is refetching that data and rendering it in our app wherever we need it. So this could be at the local level, or you can actually move this up, and React up to some type of other store, something like Context or MobX or whatever, and then your entire app is going to re-render, but you don't actually have to write any of that logic yourself. The next thing I want to talk about is conflict detection and conflict resolution. So what is conflict detection and conflict resolution? Well, basically what you want to do is provide a way to merge concurrent modifications always and in any order without any errors and very consistently. So what does this actually mean? Well, let's take a basic system that looks something like this, where we have 3 clients that are all working along the same application. Let's say we have one user creates an update, and in an offline first application, this might be an update to our local storage engine, and then we're going to then replicate this to all of the connected nodes. So this might be an operation to a half dozen connected devices, or it might be 1,000 connected devices. So then user B comes online, they make an update. These updates go to all of the connected devices as well. This is pretty simple because all we're doing is, because these things are happening along a time continuum, we're not having any conflicts. But what happens when a single moment in time gets two operations that happen at the same time? What we end up having is some type of conflict because we have two users that are writing at the same time, and their writes might be different. So this user might be updating the age, and this other user might be updating the age at the same time. So how do we resolve this? And this even gets harder when you're working with a more complex system. So say we have a half dozen or 1,000 or tens of thousands of connected devices. This, again, becomes a really tough problem to solve. And what this really comes down to is this, and how do you resolve this? The basic idea is that we want to tag objects with some type of metadata that's unique. And we want to be able to figure out, based on this tag metadata, in what order do we need to update our system, and in what order have these things come through, and which one is the winner, and who should we actually trust their operation to be the most current. And if you've ever looked at any synchronization protocols, it really just comes down to tagging these objects with metadata. There's two main schools of thought that you typically see in this discussion. The first is operational transforms. It's kind of an older idea, but Google Docs still uses it, and Microsoft Office Online. These are kind of the two biggest applications that I've found that actually still use this. And then there's this idea of CRDTs, which are conflict-free replicated data types. Redis, Facebook, Cosmos DB, those were the biggest companies that I could find that actually publicly have papers and stuff written about this stuff. Now, this stuff really gets pretty academic if you start reading some of the papers and stuff, but really what it comes down to is having a clock that's associated with the update that's happening. A clock is basically some type of unique identifier that's going to be giving some type of associative time, and this could be an actual timestamp, but it could be something that is actually more mathematical, like a vector clock or a monotonic counter, which is what we use with AppSync and Datastore. So, again, now let's look at what these clocks are actually solving. So let's take a look at a piece of data. We have a person with two properties, a name and an age. We now have two clients that come online at the same time and make an operation at the same time. Client A updates the title to engineer, and client B updates the location to Nebraska, but these operations happen at the same time. If we had a naive approach to this, we might update client A or client B first, whichever one really comes in exactly first. And then the next write would override that object, because instead of creating a merge between these two objects, what we end up doing is overriding one with the other. What we would like to have is a union between these two data sets. We'd like to have the title updated and the location updated as well, right? Now, what about with lists? This becomes even more complicated, I think, because let's say we have two connected clients. They both send an operation, and we want to add an additional item to the array of data here. Ideally, what we'd like to have is something like this, where we end up not overriding one person's piece of data with the other. We would like to have a union between the results of the hobbies array, which is ideally, what you would probably want in a situation like this. So how do we deal with this conflict detection and conflict resolution? Well, we have a couple of things that we do to make this work. First of all, we use this idea of monotonic counters. It sounds complex. It's really pretty basic, and I'm going to walk through it in just a moment. The counters and also any other versioning that we're doing is all controlled by the system itself. So this is all controlled by AppSync in a couple of different ways. And the way that we make this work is we use GraphQL types that have versions that are used for merge or reject decisions. And all this metadata is stored both locally and in the system. And then we have two tables. For every table, we have an additional change table or change journal where we keep up with all the different updates. And in the base table and in the change journal, we have this idea of time to live. And we also only operate with soft deletes. So what a soft delete is instead of actually deleting the item from the database, we add a flag that says whether or not this item has been deleted. And we'll talk about that more in just a moment, how that works. So what is a monotonic counter? They might want to make it sound like it's complicated. It's really not that complicated after I started digging into this and after we actually implemented this. All this basically is we want to have some type of counter that increments only in one direction. In our case, we only want it to increment up. We want to make sure that if we have an item stored that's version 1, it's never overwritten by version 0. We never want to overwrite version 3 by version 2. The only time you can overwrite an item is by an incremental change. So what this might look like in your table is something like this. We have IDs, we have metadata, and then we have an underscore version, and each item in the database has a version. That's the base table. What about the change table? The change journal and the change table, whatever you'd like to call this keeps up with every single mutation that happens ever in your application. Now, this has a way for us to keep up with the unique identifiers in a couple of different, well, in one way actually. And what we basically do is use a combination of our primary key and our sort key. The primary key is a concatenation of the type name, the GraphQL type name, a UUID, and the date. And the sort key is a combination of the timestamp, the UUID, and the version. And using these two keys together, we can have a unique identifier. And the way that the main way that we kind of are handling conflicts is this idea of auto merge. So let's take another look at a system that we might want to identify and find a solution to. So we have two connected clients. User B makes a mutation. She changes the age from 32 to 33. User A then gets this update. So now we've incremented the version from version 2 to version 3. I'm sorry, from version 1 to version 2. Now, user B goes offline. User B then makes an update, has an optimistic response on their UI, so to them, everything looks great. They're not back online yet, though, so the operation hasn't actually gone through. Now, user A comes back in, they actually are still online, and they make another update. So user B's update is changing the data to have an additional item called location, and they're also changing the age to 34. User A is not adding any additional metadata. They're only changing the age from 33 to 35. So we have a conflict here. Person B is updating the age. Person A is updating the age. So we have two different things that are going on here. Now, user B comes back online. What's going to happen? Well, what's going to happen is, what we would like to happen is, with auto merge, this is actually what happens, is we are going to basically take these two result sets and create a union. And what we're going to see is that when this person created this mutation of age 34, it was prior to when this other person created the age of 35. So we want to keep the location field, but we want to discard the age field. And what we end up with is this result set, where the person now has age of 35, a location of Seattle, and we increment the version to 4. And the way that we kind of do this is we use this change table, the base table, and GraphQL types with versions to deal with the merge conflicts or reject decisions. And we use GraphQL resolvers that we call sync-enabled resolvers. So auto merge is kind of the main form of conflict resolution that we, by default, would recommend. But we also offer a couple of different ways to do conflict resolution as well. Because auto merge might not be what you want for every single operation, you can kind of choose the type of conflict resolution that you'd like based on each operation. So the other options that we have are optimistic concurrency, which basically is last writer wins. And then if you want to have something custom, you can write it in a Lambda function, which is pretty easy to configure as well. So let's talk about now the synchronization piece of this. If you think of a basic approach to synchronization, you might have something like this. Your app user comes online, we fetch data from the database, and we might have 2 users that are in our system. They're both online at the same time. User 1 goes offline. User 2 sends a delete. So now we have an inconsistent data between our first and our second client. Now, when user 1 comes back online, a naive approach might be to go back and fetch the entire data set from our table. Now, this is okay in some circumstances, but really, optimally, if we're dealing with large data sets, if we're dealing with applications that are working with a lot of interactions going on the client, so single-threaded apps like JavaScript apps, but this also comes up in native iOS and Android development as well. Ideally, what we want is only to get the change set from the last time that person was online. And the way that we do this is this idea of delta sync. And delta is the change, between when the user was online last and the user comes back online. And the way that we kind of do this is by using this change table. So let's look at this again using delta sync. User 1 comes online. They fetch their data. They then go offline. Someone comes in, creates another item in the database table. But think about this maybe in its scale. This might be hundreds or thousands of items, right? What we can now do is, in the GraphQL query, we can pass in an argument. This is going to specify the last time that we synced with the database. Using this last sync argument, we can now create a query, and we can say we only want to get the changes that have happened since this last time we synced up. So now we're only going to create a query fetching the changed items, bringing those back to our device. Therefore, we're saving a lot of bandwidth and a lot of network activity, but also locally, we're not having to do as much work as well. The last thing that this gives us is this idea of time travel. Because we have an entire ledger, both of the current table, as well as all of the different operations that have happened in the past, we can actually go through our change table and see everything that's happened. So if something happens wrong, we can catch it in time before our time to live is expired and maybe see what happened. Speaking of time to live, this also gives you more optimization around your database. So using this time to live, you can set for how long you want your change journal to live. So this might be 30 minutes, it might be 30 days, it might be a year, whatever you like. After this time to live expires, the items will automatically be deleted from your database, so you don't have to pay for that additional storage. As far as the platforms are concerned, right now, as it's been for a while, the main platforms are native iOS, native Android, and web, so we support all of those. And we think that optimally, and we're seeing this a lot with our customers, people are building applications across all platforms. React Native is huge between startups that work with Amazon, but also within Amazon, where I work. We have tons of apps being built using React Native. We have our own React Native conference. We even have rewrites being done entirely in React Native because we want to deliver experiences across all these platforms. Now, React Native isn't always the answer, but it is a lot of the times. But bottom line is developers want to ship to iOS, Android, and web, and that's kind of what we want to deliver. So if you want to learn more about Datastore, you can just go to the docs. And I also have maybe a couple of starter projects on my github.com/Dabit3. And that's it. Thank you. Oh, yeah. Questions?
Does anyone have any questions?
Yeah.
Thanks for your talk. I basically have 2 questions. Is this based on local time of the device, is my first question. And the second one is, do you handle schema changes over time?
We do handle schema migrations. There's an actual utility that we have that actually will deal with the migrations. As far as the time, that's a good question because we actually don't rely on any local device time. We're using this idea of monotonic counters, and the counters are incremented based on the actual system itself. So we don't rely on any local reference to time that is created on the device itself. We're basically taking a reference from the time that the device comes online versus the next time that they update. So instead of it actually being a real timestamp, it's more of like a number. Yeah.
Cool. Anyone else have any questions?
Hi, thanks for your talk. I've got a question about auto merge. The case you showed pretty much allowed to do the merge without using the change table at all, because you could infer from the two objects that you were merging. I mean, both change properties were scalar, so you could just merge it together. How do you do it for more complex data types like lists, for example? I figure you kind of need to use the change table. And if yes, what do you do if an update comes in and you no longer have the necessary change protocol?
So we deal with lists and sets. Basically you have a couple of options that when you're actually creating the operation itself, you can do append or you can do overwrite. And if you do append, we basically are going to handle that in the resolver itself. And what we're going to basically do is basically say, we're going to have an associative time stamp, I guess you would say. It's not really a time stamp, but it's something like that, associated with every item. And then based on whether or not we feel if it's appropriate to either overwrite an item that's already there, or we'll just append to the list that's already there.
Thanks.
Yeah. We also have a big write-up / piece of documentation going into a little more depth around our conflict resolution strategy and our documentation. So you might want to check that out.
Does anyone have any other questions? We have time for one more. Okay, 3, 2, 1. Okay, you're free to go now.
Cool, thank you.